Cool. All right, so it is 3:10. So let's basically get started. Today we're going to go over some more topics with recursion. I'm going to do a couple examples, but we'll have time for some Q&A. So as I'm doing that, feel free to drop questions in the chat and so on. Before, let's see, come on Zoom. So before we really, and let's move this out of the way. Before we get into some examples, just some updates and news. So I mentioned last time that there will be no live lecture next Wednesday. Given that we're using an online exam tool, there's going to be a practice midterm that we're going to release later today or tomorrow as soon as we get it up. It won't be practice in terms of content, but it will have a couple sample questions that are just like, type in an answer here, type in your name. And the goal will be to just get practice using the CS61A exam tool setup that we're using. And then there will also be a simple Gradescope assignment to submit a practice Zoom recording. We're not going to review those Zoom recordings, but we want you to just practice like trying it out, hitting record, getting the link to the cloud recording and submitting that just in case. And as a reminder, we're not interested in hardcore reviewing the recordings. If something happens, that's okay, but they're really a backup in case any of the other auditing that we can do, such as randomizing question variable names and stuff like that. If those catch any cheating, that's really where the recordings can be helpful. But the practice assignment will just be like a minute long, and that will be 2 points. And we'll just give you credit to practice, but and the idea is that it will be due a day before the midterm. So just sometime later this week or on the weekend, if you could just practice with the tools. And then again, recursion will be on the midterm. The topics that we'll do today will hopefully give you an idea. One of the examples will that we'll go over will kind of just be to think about recursion, but won't be something that we'll quiz you on. To the question about enumerate, I can go over at the end of lecture. Enumerate is, it was an example that we've used in the past. It's not going to show up on the midterm, so I don't want to spend too much time on it right now. But it's essentially a built-in Python tool that helps sort of extract some examples when using something like a for loop. But I can come back to that at the end of lecture today. But I wouldn't worry about it too much in terms of the fact that I know it did show up on the lab study tools. And we're going to provide more examples next time. But it's not something that we're going to test you on. An example for computing the news today. This is just an interesting article, something that's pretty cool that came out a couple days ago, talking about the idea of algorithms and how they are used to inform public services. And so Amsterdam and Helsinki are the first two European cities that are launching public registries of algorithms that local governments use, or national governments, to make decisions. So if we think about things like an algorithm that might decide something related to sentencing, whether that's penalties or bail amounts, providing the information such that anyone can go in and audit how this algorithm was designed, what data was used, and so on. And so this is a really important idea because I think there's two really powerful things here. One is the fact that as algorithms become more important, they can have profound effects. And so if they're not something that we can verify, then it can be really hard to understand how those decisions are being made. The other thing that is sort of cool about this is that it just shows the power in having a wider and wider amount of people that can really understand the computer science, understand the data modeling, the statistics, any of the programming that goes into building these things. And so, one potential hope is that, if you all like programming, you'll find ways such as, various civic engagement projects to play around with some of that. So with that, today's topic, we're going to keep working on writing recursive functions. We're going to keep exploring the differences between base cases and recursive cases. We're going to play around a little bit with printing in recursive functions. And then we're also going to do some examples with lists and strings. And all of these are hopefully topics that build on the first lecture on Monday. So really thinking about when we have a base case and a recursive case, how do we get those to align to one another? Using printing as a tool to explore how the recursion is happening. And then lists are really just a way of extending that. So there are some bonus slides that I don't think we'll get to today, but we will get to after the midterm that have ways of sorting on lists, which is a cool extension. But that's where we're going today. So we talked about why recursion, and that one of the things that's really cool is that recursive structures exist in nature. And so these are all things that we can loosely call fractals. And fractals are self-similar geometric structures. And so what I'm going to do is not that zoom, is swap back over and share my terminal. Or actually, let's see. Let me switch my screen sharing over here. And we're going to play around with a really cool recursive program. And this, come on, Zoom. This should now be linked. Actually, let me change the settings. So this has video set. Cool. So this file is should be now linked on the website. It is a program that will let us draw what are a form of fractals. And the text may be a little bit small here, but this is something that the code is available on the website. You don't need to understand all of the code that's going on here. But there are a few things that this makes use of that you should be able to think through and understand. So this is a list of functions that can be drawn. And so we have a triangle, a dot, and a square. Down here are our picture drew the dot and the square. And whenever I hit space in this program, which you can play with on the website, you can run it with Python 3. -I will let us spend some time doing some interactive stuff, but the file is lecture 10 recursion 2. And this is going to tell us in the terminal just what shapes it's picking, which we'll use a little bit later. If you look at, is the screen share not, the screen share should be a little bit less blurry. Yeah, I'm recording things in two ways, so hopefully the uploaded result will be less blurry. Let me check on, no, not what I wanted. Okay, hold on. PowerPoint out of the way. Okay. Why? One sec. Now. Okay. Let me try this again. And Zoom somehow messed up my settings. Okay. let's see if we can get this to show up better. Yeah, it should work well if you minimize the video tiles and look at the screen share portion of Zoom. If my camera view is being blurry, which unfortunately I don't have much control over what Zoom is doing with that. So there should be a main white window here. And sorry if the text is a little bit small. I don't have an easy way to increase the font size right now very much. But what this is telling us is that we have a triangle, a dot, and a square that are possibilities to draw. And whenever I hit space, we're going to redraw some random shapes. And it randomly will pick a color and a shape. But what this is basically going to do is it's going to draw a V each time, and when it gets to the end of the V, it's going to pick a random shape from the list to draw. And so I'm going to hop over to the code, and this I can make a little bigger. And this will be available to read afterwards. So there's things like in this file, drawing a triangle, drawing a dot, stuff that will reset the view. You don't really need to look at any of this. What is worth thinking about is what we're doing here. So we have this draw functions list, which is a list of high order, or is itself a list of functions that we're not calling. So we're using functions as data here. And we're going to pick a random item in our list. And the question is, what happens? So I just hit the up arrow. This is something you can play with after class. So I just hit the up arrow, and now I added V to our list. Does anyone want to guess what will happen if when I hit space and draw this again? But now instead of being just a dot, a triangle, or a square, the V can draw itself. Does anyone want to guess what might happen? Or what something might look like? No takers. Okay. Yeah, it draws a family tree. So that's, we don't know exactly what it's going to look like, but drawing a tree will hopefully happen. So I hit space once. We didn't get anything very interesting. Still not too much that's interesting. So unfortunately, this is random, which is part of the challenge. And so every time we redraw this, we might have to try a few times. Why? There we go. Okay, so it took us a while, but we can see that for the most part, we just hadn't picked a random V to draw. But we did finally randomly pick one V to draw, and we got a little bit of a tree shape. And if we keep trying this again, now we randomly picked a V in this box right here. Then this branch was another smaller V. This was another smaller V and another smaller one. And so the point here, so you don't need to know how it works necessarily, but the point that this does illustrate is when we're looking at a recursive problem, and that playing around with this hopefully illustrates, is that recursion itself will come in many different forms. And so what this does think about is each of these problems is itself a smaller and more is a smaller yet similar type of problem that is being solved. In this case, instead of returning data, being drawn. We're not going to explicitly ask you about this program on the midterm, but what if you're thinking about or trying to kind of think about how to break down a recursive problem, what is worth thinking about here is when you have a recursive function, what gets called and what is the problem that's trying to solve. And in this case, we have a series of problems which each individual v is smaller than itself. So in this case, there is a question on the lecture quiz today, which is just worth thinking about, which is in terms of our recursive question or our recursive problems, every one of them still has a base case. And the base case for this question is particularly tricky because it involves something random. But there is still a base case. And so I will leave everyone to think about how the base case works, or what could be a kind of base case when we have a random function definition. But mostly what I'd say is if you're thinking about other ways of visualizing recursion, of what's happening, following along with what gets drawn, and what shapes are being called and how that works can be another way. So no, we won't explicitly ask you about this, but I do think it is an interesting tool to think about the different ways of that recursion can play a role. So with that, what I do want people to think about now is talking about printing in recursive functions. The quiz will tell you whether it's right after lecture, because I might ask one or two of them live. But the right answers will be available after the lecture. So we have this countdown function here, and this will do essentially what it says, which is if I call countdown from 10, I get countdown of 10 to 1, and then it says blast off. So now what I want you to take a few seconds and do, and let's not do that. And I'm going to drop the link in chat, but it's also on the website, is the quiz has a question, there we go, on it, which is, let's do this out of order. So 2.3. So you're welcome to take a guess in the chat as well if you'd like, but take a moment and think about if I swap the order of this countdown function such that instead of calling print first, I now call countdown and then print, what will be the new type of output that I will see in the terminal? So let's take a moment and try take a guess at 2.3. And let's see. Zoom. Let's move that out of the way. All right, so we now have most, let's see, let's see, about 2/3 of you have entered answers. So let's take a few more seconds and see. And of course, you can answer multiple times. Let's wait and see if we can get about 5 or 6 more answers in. Cool. All right, so guessing on 2.3. Let's see how this looks. So this is, right now, it looks like not quite half are guessing the correct answer. And so this is a good one to think about of what's happening. And I expect that of the answer options, I don't know what the most common incorrect option is right now. But I suspect, let's see, where did this go? Yeah, so I suspect people might have hinted at the fact that the order would be different, but that the positioning of blast off is interesting in this case. And so let's think about, and I'm going to, instead of reloading the whole file, I'm going to just paste this back into our terminal. So how should we think about processing what happens in this case? Well, when we call countdown of 10, let's say, the very first thing that we're going to do is we're going to get to countdown of n-1, so countdown of 9. And before we ever complete countdown of 9, we're going to then call countdown of 8, and then 7, and then we're going to go back up here and do 6, and 5, and 4, and 3, and 2, and 1. And so before we do anything else in this countdown function, we're always going to make another recursive call. And so then we're eventually going to get to countdown of 0. And countdown of 0 is our base case, is the last time where we don't make another recursive call. So we might expect that we print blast off first if we follow this tree from the top down. But then what happens is we need to think about, well, if once I call countdown of 10, or sorry, once I call countdown of 1, before I get back all the way up to 10, I now have this print statement. So what happens here? We say blast off, and we then count up. And so why is that, and what's happening here? So this is our base case. Once our base case returns, we're now essentially in countdown of 1, and we can sort of verify this just by calling on its own. And then once countdown of 0 returns, then we print, and then we're in countdown of 1. And once countdown of 2 returns, then we finish countdown of 1, so that printed, and then we're in the 2 function. And so this is to say that, so 2 questions here. First, why do we get to 10 when n-1 is 10? So the reason is we're still printing n. When we call countdown of 10, if this middle line here never happens, we would still print the number 10. And so that is how that's how the last 10 still gets printed, is that this function still gets to be called and executed in the way like any other function does. And after that function finishes doing whatever it does, then this print statement happens. So then the question is, so how do we go from 0 to 10? So what's happening here is as we finish, when we do countdown of 1, what we first call. Let me actually move this so it's over on the side here. And for the recording, I will move that. When we have a countdown of 1, what we do here first is we have countdown 1. Let's uncomment this. This becomes countdown of n minus 1. So we have a countdown of 0. And actually, let me just draw this out over here. So you can imagine that we have countdown of 1. This then gives us, and actually, so this is a valid Python file. I'll start here. This then gives us countdown of 0. And countdown of 0 is going to return, or it's going to print blast off, and then it returns and stops running. And then what we have next beneath this is print of 1. So within countdown of 1, we make this this sort of tree where we call 0, then we do our print. And then if we were to imagine before, if we had started with countdown of 2, and I'm going to shift all this over. That didn't tab in the right place. That's okay. We're going to have the same kind of setup where after each, what's going to happen here is we're going to first make a recursive call, go all the way down, and then we're going to print. And so when we print afterwards, we start counting back up. And what's worth thinking about here is the best way to probably illustrate this is if we print our n value both before and after our recursion. And so what you should think about here is as we're working on computing data, so this one is not computing anything, which is why it is a useful example for thinking about where n is and what is happening with this value of n before and after. And so I'm just going to do 5 just to give us some data. But what we can see when we do and I'll do Python tutor in a second. And let's see. I don't know if I can actually control what is pinned for everyone. But if we do countdown of 5, when we look at this, the print both before and after a recursive call will hopefully illustrate what's going on here, which is that we have in each recursive call, or within each sort of countdown call, we start off with our n, then we make a recursive call. And we keep making recursive calls all the way until we reach, let's pull this back up, blast off, which is our base case. And then afterwards, as those functions return, we still have to finish countdown of 1. We still have to finish countdown of 2 and 3 and so on. And so that that piece of recursion is something that can be really useful. It's also something to keep in mind that as we return, we still have to finish each of these function calls. And so there's another example in lecture, but I'm going to pull up Python tutor for this. And so let's see. So if I visualize, that is not going to be helpful if I don't actually call countdown. So if we again try this on 5, you'll note that Python Tutor gives us a lot of steps. So I don't want to go through every single step that we have, but we will kind of think through this. So when we're working with Python Tutor, and let me make this a little bit wider. So far, good as normal, we create our function. When we're in countdown, we have a frame f1, which is our first call to countdown, and is 5 because that's what we pass in. And as we step through this, you can see that we print 5, and then whenever we call countdown of n minus 1, we end up with a new frame where n is 4. And so for each of these, we're going to keep going through. We check our statements. We keep entering a new frame. And so we keep going down our stack until we get to n of 1. And finally, we'll have our last call to countdown is we print our 1, then we have our countdown of n is equal to 0. And so what's worth thinking about here is we get to n is equal to 0. This will be our last step here. We'll print blast off. And then note how in Python Tutor, this is one of the things with recursion that can be a little bit subtle and where the visualization is not perfect. But until a function in Python Tutor has a return value, we are still, we have that function open in a sense where Python is still evaluating this function. And so what happens here is we only after we return none, because that Python is always going to return none if we don't specify something, but in this case we're not using the return value, so it doesn't really matter. We then go back up to this frame of where we're now with n equals 1. And as we go through, we'll note that Python Tutor keeps showing us that we return none, and it turns them into gray. Whereas right now, it can be a little bit subtle, but these are, while you're running through it, these are darker because they're sort of in the middle of being executed. And so what happens is until every time we make a recursive function, that original call, so that first n equals 5 call, and then later that n equals 4 call, those functions are still active while all this stuff below is being executed. So we haven't finished our n equals 5 call until the very end. We haven't finished our n equals 1 call until we have also finished n equals 0. And because of that, what we're now happening is we go all the way back down, and then once we get to our base case, we start going all the way back up. Sometimes we call this a stack, which is sort of a technical term. We're not really going to get into all the details of it in CS88, but you can think of this as a stack of functions that as we go down, we have, in this case right now, we're in the function for n equals 3. We just finished printing the after 3 line. So we're about to return none. When the n equals 3 function returns after right here, when we're done with it, we are now inside the body of the n equals 4 call. So this would be sort of our second step of our recursion. And so we print 4 because that's the last line of that function. And then when 4 returns, we're back inside our call for our original countdown where n equals 5. And so once we're back inside the n equals 5 call, we then make our print, it returns none, and then we're finally done with our with our bit of code. Python tutor, one of the things that would probably help is if this stack of functions were sort of indented as we went down, is typically how we might draw this as being more clearly sort of nested within each other. But they still happen in the order that they appear, or the functions are still called in the order that they appear on Python tutor. So we'll do one more example thinking about this. So the first, let's do sum of squares. And I have sum of squares is also in the slides, so you can review this later as well, more easily at least. So if we do sum of squares of 5, if I copy, wait. Why did it not grab? Oh, because this is a typo. Whoops. We'll fix that. Interestingly, no one caught that the last 2 times that this has been used. Are you kidding me? Okay, Python, hold on. No, not that. Okay. Why? Okay, one sec. Let's try this again. Okay, let's stop that. Let's see if we can get sum of squares to work. Okay. Cool. Now sum of squares should work correctly. So in this file there are two sum of squares defined, and they work, or they do the same computation, but one also will print the values as they're going on. Oh, what did I do? Okay, let's fix the parentheses. Oh, darn it. One second. This one is also broken for some reason. Okay. And actually, that is not right. This should be recursive. So we'll try this again. Live coding. Okay, so we'll verify that sum of squares still works, and now we'll call the print function. And so one of the things to illustrate with using print in recursive functions is that it can get, you have to be careful about what step of the recursive function you're in. But we first start off with like normal, n is equal to 5. And let's pull this back up. In this one, we're going to compute our squared value first, just to show where, what step we're on. So 5 squared, 25, that's all good. And then what gets returned is the result, so 25 plus n is equal to 4, and which would be 16 plus n is equal to 3, all the way until we get to n. And what this doesn't show necessarily right here is the result right after the recursive call, because we do it in one in one step. Homework that will be due, there will be homework due at the end of next week. It'll just be completing a practice midterm. So that should be up later today, and it will be based just on effort. So as long as you turn in a practice midterm, we'll have info on that up, if not later today, then tomorrow. But you'll be able to also turn it in after the midterm if you really want to. Yeah. So, what is the base case of sum of squares? That's a good question. The base case is the line where we don't make a recursive call. So in this case, whether or not we're printing, the base case is n is less than 1. There are previous midterms, and then we'll be releasing some sample problems that we wrote but didn't use for this midterm. I don't know. The TAs will make a note about which, if we want you to do a specific midterm or just any midterm, but we will. There are linked on the website previous midterms as well, as we'll be putting out in a day or so some sample questions that we wrote but didn't use for this midterm. Yeah, so in this case, for sum of squares, the base case is n is less than 1 or n is 0. The main reason that we might write something as n is less than 1 is if I write sum of squares and I were to write something like -6, by writing n is less than 1, I would get 0 as a result. If I were to write this, so this is a good thing to think about, which is if I write this base case as n equals 0, so I do sum of squares of 5, and I get the same result. Now my base case is n equals 0 in this sum of squares function. So when I execute sum of squares of -6, does someone want to guess what will happen? So we have a vote for 0. It'll keep looping, error, infinite loop. Okay, cool. Yeah, so all these are good guesses. It will do, depending on what your, how precise you want to be, more than one of those is technically correct, which is we do keep looping until Python gives us an error, which is maximum recursion depth exceeded. And what this means is that as we keep making recursive calls, that Python at some point will think that an infinite loop has happened, that we would never get towards our base case, and so it will throw an error that stops your program for you to prevent your computer from essentially just wasting processing power. The more clear way of sort of seeing what's going on is if we change, and I will put these back to the real, the real versions after lecture, and the fixed version will be on the website. But if we print it, we'll get to see what happens here. And so when we print with something like -6, what we're first going to try and do is compute the square of -6, which we can do, right? That's just 36. But then we'll, instead of working our way towards 0, -6 minus 1 is going to be -7. So as we print this, what we'll see is happening is our squares, instead of going towards 0, will just be increasingly smaller negative numbers, and that's one of the things to be aware of when we have a base case with different kinds of inputs. is the place that we are using recursion, so n minus 1, is this working towards our base case? And that is going to be one of the most critical things to practice with and to think about, which is for most inputs, and we're not going to, it will be clear what we're asking you to practice on, and for the most part, in an exam setting, we're not going to give you something intentionally tricky. So if we give you a series of doc tests, then your job is to pass those doc tests, and you don't need to worry if there is, a particularly tricky base case or something else, as long as your function answers the prompt. But what is worth thinking about as you're working on functions is, does my input, the base case, and the way that I'm dividing the problem in recursive steps align? Yeah, so if we wanted to make recursive, or if we want to make negative numbers work, and we could definitely do something where we could say, elif, this is a good suggestion, n is less than 0. We could do n plus 1 such that we work our way to 0. There's a lot of other things that we could do. An interesting trick, because squaring a negative number actually works, it will just be adding. Since we're adding and squaring, squaring -6 is no different than what do you call it? Than just squaring 6. We could even do n times -1 here if we wanted to not repeat the entire return statement, so that we just change the input to be positive. Depending on the problem definition, there are a bunch of different ways that we could solve this statement or this problem. But you're totally right that we could do this. We could, assuming I define squared, but replacing this with a plus 1 over here, both those would be basically equivalent, do the right job. It really depends on how you wanted to solve this particular problem. So before we leave, what I will just mention is the slides go through a couple other problems where we did not talk about this in lecture today, but it is worth thinking about. There is a question using strings in the practice quiz, but recursion itself also works on. Let me actually make this. So I hope Zoom did not break my PowerPoint slides. But if we want to, we can also do recursion over data in a list or a string. And so one of the things to think about is when we're working with a list, if we want to find something like the minimum element, we can separate out our base case for lists and strings. And with numbers, it will often be something like n is equal to 0. With a list, it's often when we only have one or no elements in our list, depending on what the particular problem is. And so this problem is also in the lecture slides, or in the Python file. It is right here in the lecture slides. But thinking about how do we break down a question of finding the smallest item in the list? Well, it's the smallest item between the first item and the smallest item in the rest of the list. And so this is a problem that I would encourage you to read and practice with as well. You can play with it in this Python file, 156 7, -3. The function works as defined, but to really go through and think about what it's doing by breaking a list into the first item and the rest, there is a very similar process that we're not going to walk through all the steps, but there is a function, and this is one of the quiz questions, which is to figure out how we can reverse a string. And so this also will work by separating a string into two parts that each work towards the base case. Python's built-in min function is more clever. It doesn't use recursion. It has some built-in optimizations. So if you're actually doing this on a large data set, you would want to use the built-in min function, because I can just pass in I can already just pass in a list to Python's min function. So if I were doing it in a real scenario, there's no need to define your own recursive version. But it does illustrate one way of thinking about breaking up a problem. And with all of these cases, what we're really trying to do is find a base case, which is often a very small list, and then split up the list into two pieces, which typically is a first half and a second half, one item and the rest of the list, the first item and the rest, the last item and everything except the last item. All of these are acceptable ways of splitting up our list. So that is that's another way of thinking about recursion. In the slides, we walk through it with printing, but there are also examples for the environment diagram of sum of squares. And then there is a link on these slides to play around with that as well. So if you want to review another example, that is where I would go to do that. And then the last thing that I wanted to just get back to is, let's see where, if I can pull this up in a new window. Okay, here it is. Yeah, so in Python, enumerate one of the best examples, and we could try this out in a terminal in a second. Again, this is not something that you need to know for the midterm, but it was at the beginning of a class, so I did want to come back to it. Whenever we have a question about what's going on in Python, the first or one of the best places to get help, if it's not in something like a lab or a lecture or homework, is to go to docs.python.org, or if you just Google for Python enumerate documentation, it's there. But you can type enumerate in the search box, would find this page, and in here, Python gives us some examples of how we can use enumerate. And this example uses some Python syntax that we haven't gotten to yet. But what is useful is the first example. So I'm just going to copy and paste this here, just because I don't need to type it again. And remember how with map we got a special map object back? Enumerate actually works the same way. It gives us an enumerate object. Again, not something you would necessarily need to know, but that does make it useful in a for loop. We could like the way that we could write a loop over map, or we can even map technically over the result of enumerate. All these things that give us back a sequence of data. We can we can basically just work within a loop. The way that I would figure out how enumerate works, if I also didn't have the documentation, but let's say I knew that enumerate would work on a list, is to just try calling enumerate seasons. And when I see a result like enumerate of an object is to take a for loop and to say for thing in enumerate seasons, print this thing back. And all enumerate is doing is giving us back the items of our list along with the index of the items of our list. So it's doing it one sort of step at a time. But if we ever need to know the item and the position of our list together, that's a good use for enumerate. But we could also say for index in range lane seasons, print, index plus, we need to convert things to a string in Python, and I'll give some space, and we'll say seasons index. And so if we wanted to do something manually, we could skip using enumerate, just get the index from a range and print things out that way. And really enumerate is just making a pattern like this a little bit simpler because it is sometimes a common pattern that we'd use. So yeah, that's it for today. In terms of recursion in general, for anyone still watching, the main thing is to just keep practice with recursion. Think about what our base case is, what is potentially a reasonable base case, and as we divide our program and our problem to make that be something that we work towards the base case, are we always breaking that down in the right set of steps? So that's what I practice with. There are a couple questions today on the lecture quiz that help you think about what are possible base cases or what are possible recursive cases. And just as a hint, the questions kind of suggest it, but there's often more than one correct solution to writing a good recursive case, or there's more than one way to break a problem down into smaller parts. So just think about that as you're working through the questions on the quiz. And again, remember that for all the quizzes, you can answer them as many times as you want. As long as you answer them once before the deadline, you'll get credit for doing them on time. So if you've missed questions earlier in this semester, you can go back and play with your answers as well. But yeah, that's it for today. Yeah, if you have any questions, I can hang on for another minute. The quiz, okay, so now that we're after the quiz will now show the correct answers, but I don't have explanations in there yet, so I'll add them in later today or tomorrow. But the correct answers will now be shown for the quiz. All right, thanks everyone.